Chapter 2, Atoms, Ions, and Molecules, Part 3. All right, water. We were talking about the properties of water. Well, one awesome thing is water is a great solvent. So water is great for dissolving things, especially things that are charged in some way. So nonpolar molecules and charged substances dissolve in water. When something dissolves in water, it is called a solute. So a solution for this course is water, the solvent, dissolving things, the solutes. So again, for this course, our solvent's always going to be water because the human body is mostly water. So some substances that dissolve in water are then called hydrophilic. Hydrophilic, water-loving, they're going to dissolve in water. They can then form electrolytes if they formed charged particles, charged ions, or they are non-electrolytes if they do not form charged particles. So glucose, sugar dissolves in water, but is not an electrolyte, but say sodium chloride does dissolve in water and form electrolytes. Nonpolar molecules do not dissolve in water, so water is not truly a universal solvent. Things that do not dissolve in water are called hydrophobic. Hydrophobic, water-fearing. So instead, those hydrophobic molecules will collect together to try to avoid contact with water. There's hydrophobic exclusion. And they'll interact with each other and try to keep the water out. And so substances that are important for our body that are hydrophobic end up having to be carried by special protein carriers around in the bloodstream. So fats, cholesterol, things like that. Amphipathic molecules dissolve partially in water and partially avoid it. So what happens is we have the charged polar portion facing out toward the water environment, the aqueous environment, and the nonpolar fatty acids in this case facing in away from the water. So for instance, phospholipids form a bilayer because the phosphate heads that are charged face out toward the aqueous or watery solutions in our body, and the fatty acid chains, the nonpolar chains, face in, so you get two layers. So water does a lot of amazing things. Cushions for our structures like the brain, transports materials, lubricates to reduce friction and prevent damage, affects surface tension to determine how much the water should pull, P-U-L-L, on delicate structures, function as a neutral compound, pH-wise, and then water can help regulate body temperature. So when we sweat, the water evaporates off of our skin. When it evaporates off the skin, it pulls heat with it away from the body. It dissolves many, many things. It dissolves all the hydrophilic various substances and partially attracts at least the amphipathic molecules, but not hydrophobic molecules. They do not dissolve in water. All right, so water can on occasion dissociate into ions. This is rare, but it can happen. So water can become positively charged water, H3O+, and negatively charged hydroxyl group, OH negative, which is often simplified into H2 yields hydrogen ion plus hydroxyl ion. And so obviously when they come together, it becomes the neutral water. Again, the arrow here is pointing at the product. So we have the reactants or leading to the production of the products, the lovely chemical equation there. Acids are electrolytes that dissolve in water and produce a hydrogen ion and an anion. So acids generate hydrogen ions. So for instance, hydrochloric acid will dissolve in water to form hydrogen ions plus negatively charged chloride ions. Bases, on the other hand, dissociate into electrolytes that will be able to bind to a hydrogen ion. So they're referred to as proton acceptor. So for instance, sodium hydroxide here will dissolve into sodium ions plus hydroxide ions. Then the hydroxide ion plus the hydrogen ion leads to water. So bases produce proton acceptors, things that will bind to free hydrogen ions. pH ranges from 0 to 14. The lower the number, the more acidic something is. So pH 1, extremely acidic, for example, hydrochloric acid. pH 14, extremely basic or alkaline, such as sodium hydroxide. And we see a lot of common things go throughout the range. Pure water is 7. 7 is considered neutral, so pH of 7 is neutral. Milk is a little acidic. Wine is very acidic. Seawater slightly basic. Bleach pretty basic or alkaline. Neutralization. Neutralization is when an acid and a base are put together, and that gets rid of the pH and turns it into a pH of 7. So making an acidic solution or a basic solution become a pH of 7. So acids were neutralized by adding base to them. Bases are neutralized by adding acids to them. Get the right amount added, and you'll get a pH of 7, the same as pure water. So for instance, medications like antacids, people take those to neutralize the stomach acid so that the environment in the stomach becomes neutral rather than remaining acidic. Buffers. Buffers are very important in our bodies. Buffers help to prevent changes in pH. So whether you're adding some acid or some base, a buffered solution will resist the changes to the pH. So for instance, here's this lovely example of adding hydrochloric acid to something. If you add it to pure water, the more you add, the more acidic the water will become. Pretty linear there. If you add it to a buffered solution, though, it takes a while for the hydrochloric acid to overwhelm the buffered solution and start to become significantly acidic. And that's ideal, say, for our blood. We want our blood's pH to stay within a narrow range, so blood is buffered so that if we get some acid or base added to the blood, there is not a dramatic change in pH. It stays within that narrow range. And that is using carbonic acid and bicarbonate within the blood to buffer the blood. Mixtures. Mixtures are when you mix two or more substances together. A mixture, it does not necessarily mean you have a solution. So a solution is a subcategory of mixtures. Mixtures can be suspensions. Suspensions mean you have something big mixed with fluids, and those big things can easily settle out. So you take blood, you spin it in a centrifuge, and the cells of the blood will easily separate out because they're very large and they're just suspended there. A colloid is a mixture where you have small things within the fluid, and they do not settle out. So proteins in our blood do not settle out. So when they put blood in a centrifuge, the proteins don't form a layer. They stay evenly mixed in with the fluid components. And then finally, solutions is when you have solutes dissolved in, and they're small enough that they do not scatter light. So the fluid remains relatively clear, light is not scattered. So electrolytes in the blood don't come out from being put in a centrifuge and don't scatter light. Also, we know you can mix oil and water, mix them up, and it looks interesting. It's kind of pretty to look at, but if you just wait over time after you're done mixing, they will automatically separate out. So it takes motion to keep the oil mixed in with the water, and that's referred to as an emulsion. So we won't do much math in this course, but we will see things like mass over volume. So amount of iron in blood should be 40 to 150 micrograms per deciliter. We'll see mass over volume. So you'll say we have a solution that's 5% dextrose. That means there's 5 grams of dextrose per 100 milliliters of solution. And we might talk a little bit about molarity and molality. Again, you need to just remember what these mean, but we're not going to really do any math involved with them. Oh, and the mole, not that mole, this mole, 6.022 times 10 to the negative 23rd atoms. That is how many atoms is in the molecular mass of an atom. So hydrogen's molecular mass is 1.008. So that means if you have 6.0022 times 10 to the 23rd atoms of hydrogen, it'll be 1.008 grams. So different atoms have different molecular atomic masses, which are the same as molecular masses, except molecular masses are for molecules. So if you wanted to figure out the molecular mass of carbon dioxide, you would add the atomic masses of carbon and 2 oxygens to get the molecular mass for the molecule carbon dioxide. Again, we're not going to do much with the mole, just wanted to remind you that it exists. Organic molecules. Organic molecules are extremely important because we are made up mostly of organic molecules. And organic means it has carbon and hydrogen. Carbon and hydrogen. May have other elements present, but it must have carbon and hydrogen. Our large macromolecules, carbohydrates, proteins, lipids, nucleic acids are all organic molecules. Inorganic molecules is everything else. So inorganic molecules do not possess both carbon and hydrogen. Might have one, might have the other, does not have both. So for instance, in this mixture here, we see carbon dioxide is inorganic, water is inorganic, methane is organic, has carbon and hydrogen. Glucose is organic, has carbon and hydrogen. So you get the idea. Again, often macromolecules are shown as carbon skeletons where you don't really see the carbons that well. One thing that happens with the macromolecules, though, is we often have what are called functional groups. Functional groups are things that are the reactive portions of an organic molecule. So they might be polar, they might be able to form hydrogen bonds, they might act like acids, they might act like bases. They have different special chemical properties they bring to a larger organic molecule. So here is a simple amino acid. The central carbons attached to an amine group, which acts like a base, and a carboxyl group that acts like an acid, and a R group, which is another functional group that is different from amino acid to amino acid. So it could have different chemical properties. Here is some common functional groups: hydroxyl, carbonyl, amine, phosphate. Some of these are important and will come up again and again: carboxyl, hydroxyl, amine, phosphate. There's some others that won't show up that often. Again, know they exist, that they change the chemical properties, but we won't go into too much detail about them. So, biological macromolecules. Again, macromolecules in our biology are all organic, so they have carbon and hydrogen, often oxygen, often nitrogen or phosphorus or sulfur. Again, so they will be more complicated, but they always have carbon and hydrogen. We can again form them in lines or rings, as I showed earlier. And there are a few out there that are just hydrogen and carbon, so those biomolecules would be hydrocarbons, and hydrocarbons with just carbon and hydrogen are always nonpolar, always hydrophobic. Just carbon and hydrogen is nonpolar and hydrophobic. Think about those phospholipids again. All right, monomers. Monomers are a smaller subunit that comes together again and again and again, the repeating subunits again and again and again that lead to the macromolecule. So, for instance, amino acids are the monomers for proteins. So tons of different amino acids come together in a long chain of amino acids to form the proteins. The monomer for carbohydrates, often called simple sugars, also called monosaccharides. Again, you have those monosaccharides forming a chain, one monosaccharide after another, after another, after another. For nucleic acids, the monomer is the nucleotide, lots, thousands or more nucleotides in a long chain to form the nucleic acid. So 3 of the 4 most common biological macromolecules are made up of monomers. The one exception to this are lipids. Lipids are not made up of monomers. And we'll be talking about these macromolecules in more detail in the next lecture.